You get copper 2 or copper 1? Copper 1 nitrate or copper 2 nitrate? Copper 1? How come copper 1? Why not copper 2? Well, when copper metal is oxidized, does it go first to copper 1 and then copper 2? Or does it go straight to copper 2? Straight to copper 2. When tin gets oxidized, does it go straight to tin 4 or to tin 2? It goes to tin 2, and then the tin 2 goes to tin 4. When iron gets oxidized, does it go straight to iron 3 or to iron 2? Iron 2. So this is how we know. Copper goes to copper 2 nitrate, not copper 1 nitrate. Copper 2 nitrate would need 2 nitrates to balance out the copper. And silver, elemental silver, which is Ag solid, silver metal. And then we'll compare the activity of silver and copper metal. So here's silver metal, here's copper metal. Which one's more active? Copper. More active, less active. Less active is more stable. So there's a driving force this way. So we expect reaction. If there's going to be a reaction here, let's go ahead and balance it. It's not balanced. One copper, one silver, one nitrate, 2 nitrates. So we'll need 2 of these. It's going to give me 2 silvers here. I'll need 2 silvers there. Balance. And this would be the CE with the driving force. Now let's go to the IE. So for IE, is that a strong acid? Copper metal? Strong base? Soluble salt? No, so we move on. Strong acid? No, strong base? Soluble salt? Yes. So 2 silver ions plus 2 nitrate ions. I'm going to make sure we have a balance. For every silver, there's going to be a nitrate. So if we have 2 silvers, we're going to have 2 nitrates. Is this a strong acid? No. Strong base? Soluble salt? Yes. So that's going to give a copper 2. For every copper 2, we've got to have 2 nitrates. Balanced formula. And then strong acid, no. Strong base, no. Soluble salt, no. So silver will just leave alone. Are there any spectators? Yeah. What is it? Yeah. 3 minus nitrate is spectator, so let's get rid of that. Net. So copper solid plus 2 silver ions yields copper 2 plus 2 silver metals. In other words, copper is a reducing agent, the silver ion is the oxidizing agent. Going forward. Okay, what was the next reaction in experiment 6?
After this one?
Yeah.
It was copper is added to hydrochloric acid.
All right. Copper is added to hydrochloric acid. Copper metal plus hydrochloric acid is HCl. Except our copper is not pure copper. Our copper was contaminated. The surface of our copper had a coating. That coating just forms naturally. So, for example, if I have pure copper here, and then I have some air up here, eventually what's going to happen is the surface layer is going to become oxidized. So we'll generate a thin coating of oxide on here. Initially, we'll generate copper 1 oxide. What's the formula for copper 1 oxide? Well, we call it copper, Roman numeral 1, oxide, not oxygen, but oxide, as its name. What would the formula be? Cu2O, solid. If we give it additional time, this forms a red coating. If we give it more time, then the copper gets further oxidized. And that coating will turn black. What's the formula for copper 2 oxide? CuO. And so, initially when we look at our copper is susceptible to oxidation. So we have two choices. One, we could clean it off. One recommended method for cleaning this off is to sand off the oxide layer. But we don't do it. Another way is you can remove it chemically. So the first reaction, when you pour HCl on here, it doesn't contact the copper. It'll contact copper 1 oxide or copper 2 oxide, depending on how old this copper is. So that's the first reaction. So the first reaction is going to be, let's say copper 2 oxide solid plus HCl. Is that a single replacement reaction? No. What type of reaction is this? This is a double replacement. AB plus CD, so we have two compounds. And what should form here? Copper 2 chloride, which is going to have the formula CuCl2. And hydrogen oxide. What's hydrogen oxide's formula? H2O, aka water. Is there a driving force for this? Chlorides, bromides, and iodides are all soluble except for silver, lead, mercury, so this is soluble. Are we going from stronger acid to weaker acid?
Yes.
Yeah. HCl is a stronger acid, water is a weaker acid. So stronger acid to weaker acid, this is our driving force. We have driving force here. If we got driving force, I might as well balance this. H2O is going to be a liquid, so we got one copper, one oxygen, one hydrogen, two hydrogens. So we'll need two HCl's, and then it's balanced. So what's happening here is the copper oxide layer is being eaten away by the acid. If the copper oxide layer is being eaten away by the acid, then this is a black coating on it. What's going to happen is it's going to get a shiny copper. In other words, the luster of metallic copper will come back. The same thing, if there's a red copper 1 oxide coating on there, solid, the HCl will also eat that up. What forms here? Well, it's going to be copper 1 with, and hydrogen with oxide. So copper 1 with chloride is CuCl, is +1 -1, and hydrogen oxide is water, H2O. And so again, this is stronger acid to weaker acid. And so what's going to happen is the solid layer of oxide is going to be eaten away, dissolved by the acid. So once I dissolve the oxide, then I'm going to be left with copper metal, bright, shiny copper metal. This is actually how we, used to, if you go get some taco sauce, like Del Taco or Taco Bell or something, and you put your pennies in the taco sauce. Have you ever done that? You put your pennies in the taco sauce and they come out like looking like brand new. They come out looking like brand new because taco sauce has acetic acid, vinegar, and the acetic acid's acid. Acids will attack the oxide here and make water, which is a weaker acid. So acetic acid goes to water. And so we don't have to use hydrochloric acid, we can use acetic acid. It'll eat up the oxide and leave you with a fresh surface of copper metal. Now the copper metal will be attacked by hydrochloric acid. or even acetic acid. So let's try it here. When we look at this, what kind of reaction is this? Single replacement. So this follows the A plus BX pattern. And what are we going to form? Are we going to form copper 1 or copper 2 chloride? We're going to form copper 2 chloride, according to the redox chart there. And hydrogen H. How we tell is they just look at the chart. The chart's going to tell you the copper is going to go straight to copper 2. It doesn't stop at copper 1. If it went from copper to copper 1 and then copper 1 went to copper 2, then we go to copper 1. But in this case, it just goes straight to copper 2. In these types of reactions, it's like iron. Does, how do I know that iron goes to iron 2? Well, iron goes to iron 2. And then eventually the iron 2 will go to iron 3. Well, what we're doing is just doing the first step. And then eventually the iron 2 goes to iron 3. So it makes it complicated because we can form multiple products. It's like when you burn methane. Of course, when we burn methane, we'd love to form CO2. We don't want to form any carbon monoxide, and we don't want to form any soot, but that often happens. How many people die from carbon monoxide poisoning every year? It's like 10 to 100 people per year die from carbon monoxide poisoning from poorly adjusted burners. Water heaters, mostly, I think. That's why, in some buildings, carbon monoxide alarms are required. They're required because, of course, we want to form carbon dioxide, but sometimes we form multiple products. And so if that's the case, which one should we choose? And so this is what I told you. In general, we just try to do complete oxidation. When I ask you for the equation to burn methane, you might say, well, what do I form? Do I form soot? Do I form carbon monoxide? Or do I form carbon dioxide? Well, in general, just go complete oxidation. And so in general, we would go straight to copper 2. That's a general rule of thumb, but rules always have exceptions. And so, one exception would be iron. Iron does not go straight to iron 3. Iron goes to iron 2, and then iron 2 goes to iron 3. So, that's the exception. So here, we're just going to go straight to copper 2 chloride, and hydrogen. Well, hydrogen is not stable as an atomic element. It is a diatomic, so we need H2 here. And then we're going to compare copper with hydrogen. Which one's more active? Copper or hydrogen? Hydrogen's more active. So what we're doing is we're going from a less active, more stable, to a more active, less stable. Is that the right way? No, actually the driving force is reversed. And so in the forward direction we get no reaction. And so you might have noticed some reaction take place, but it wasn't redox. The reaction that you might have noticed taking place is that the copper metal was clean. The surface oxide was eaten away by the acid, but the underlying metal was not eaten away. So you could leave your copper in the acid and nothing's going to happen with the hydrochloric acid and copper. It's not going to react. All right, what's the next? Zinc is added to hydrochloric acid. This is how you make hollow pennies. Hollow pennies, because pennies on the outside are copper. But on the inside, we have zinc. Zinc metals on the inside. And so the hydrochloric acid does not attack the copper. It's an unfavorable reaction. Hydrochloric acid and copper, we get no reaction. But hydrochloric acid and zinc, we do get a reaction. I did this one in class earlier. We're going to form zinc chloride and hydrogen gas. There's a reaction here because which one's more active, zinc or hydrogen gas? It turns out that zinc is more active. Zinc is more active than hydrogen. So we're going from more active to less active. And so the hydrochloric acid, it eats up the zinc, dissolves it to form zinc chloride, but it won't touch the copper. So what some people do is they put a little nick in here. They rub off some of the copper to expose the zinc, and then they let the penny sit in hydrochloric acid. And the hydrochloric acid will eat the whole interior of the penny and just leave the copper exterior. So you can make. You could also use vinegar, do the same thing, or taco sauce if you left it in taco sauce for a long time. Do the same thing because acetic acid will do the same thing. If we have zinc plus acetic acid, we're just going to form C2H2. We're just going to form zinc acetate plus hydrogen. So again, we're going from more active to less active. Okay, so I guess we're out of time. For the test, the request was, I was thinking about putting just simple single replacement reactions on the test, but I think most people didn't want those. So we might just end up going to metathesis and acid base and stop there for the test on Thursday and have no single replacement. But if I put single replacements on the exam on Thursday, they would be simple ones, no exceptions. So think about that.